SwayamPrabha. Digital India. Educated India.
In this lecture, let us continue our discussion on high temperature gas dynamics. We will recapitulate the boundary layer calculations for a flat plate that we did in the previous lecture, and then we will recapitulate some of the basic thermodynamics concepts which are relevant for the upcoming lectures. We would briefly look at perfect gas equation of state as well. In the previous lecture, we had dealt with two cases, if you recall. So, there was a case A where we immersed a flat plate of dimensions 1 by 10 meters chord by span in uniform flow at sea level conditions with m infinity equal to 8 and insulated wall. And we found that the heat transfer rate comes out to be 55 watt per centimeter square. We also took note that it is comparable or maybe little more than the stagnation point heating that the Columbia Space Shuttle used to face during atmospheric entry, which is a huge amount of heating. And therefore, when we expose a slender surface like a flat plate at sea level conditions in a Mach 8 flow, then the aerothermal environment becomes very severe. If the Mach number increases further, the heating will be enormously increased, which is absolutely unsafe for the vehicle, and probably the vehicle will get affected due to the enormous heating. And therefore, there needs to be some alternative way of handling this, and very often the strategy was discussed over here was that we need to slow down the vehicle at higher altitudes where the atmosphere is thinner and the heating rates are dramatically reduced. In order to establish that, we also did a case B calculation where we exposed the flat plate to free stream flow at 15 kilometers altitude, and when we did the calculations with an isothermal wall, we found that the heat transfer rate was much significantly reduced. Also, the drag came down. We found that the drag became about 29% of what is encountered at sea level, and we saw that it is basically due to the lower density values as well as drop in the V infinity values, because the A infinity reduced at higher altitudes due to T infinity reduction, and if we were flying the flat plate at the same Mach number, the V infinity will be significantly reduced, and consequently put together they would end up reducing the drag value. When we looked at the heat transfer calculations, maintaining the same condition as the case A, that is wall to free stream temperature ratio being 1, and we got the Stanton number values from the chart. We did the calculations and we found that the adiabatic wall temperature came down significantly, and we further saw that when QW calculations were done, the values came down much below what was encountered at sea level conditions to about 25% value at sea level, and therefore, it is well understood that even if m infinity is beyond 8 at 15 kilometers altitude, the heat transfer rates are not going to be significantly high, and therefore, in the outer reaches of the atmosphere at much higher altitudes, things will be even more favorable. However, we understood that very high temperatures are to be encountered at these kind of hypersonic conditions, and there is no alternative out of that, and therefore, we need to understand what happens to the state of the air or the working fluid when it encounters high temperatures. Inevitably, it would start reacting, and then we need to talk about high temperature gas dynamics, and therefore, we need to gear up in order to address those issues. So, in the next few slides we are going to start discussing and recapitulating some of the thermodynamics aspects which are going to be handy for us to address high temperature gas dynamics subsequently. So, we begin by discussing about perfect gas and real gas. Most often in our kind of discussions here, we are going to deal with perfect gas, that is a gas in which intermolecular forces are negligibly small, and the equation of state for such a gas could be given in one possible form like this: P into small v equal to R T, or P is equal to rho R T, where small v is specific volume, rho is the density, and specific volume is the inverse of density, and R being the specific gas constant changes from one gas to the other. For air with a molecular weight of around 28 units, we get from the universal gas constant by dividing it by the molecular weight of air, we will be able to get the specific gas constant, and we are going to discuss about their values in the subsequent slides. I am not elaborating that right now. Coming to real gases, a real gas is one where intermolecular forces are important, and under what conditions do they become important? It is very high pressures of the order of thousands of atmosphere, or very low temperatures, maybe in terms of few tens of Kelvin, close to absolute zero. Under these conditions, basically what happens is that the gas molecules become highly packed, and they are very close to each other. Therefore, the intermolecular gaps are much reduced, and they also possess very low inertia. In such a situation, the intermolecular forces, they do get a chance to act on the molecules, and consequently they modify the macroscopic properties of the thermodynamic system comprising of that gas. Consequently, the equation of state becomes quite different. So, compared to what we had earlier for the perfect gas P v equal to R T, you see both of the pressure as well as the specific volume term getting altered. So, this is like modified pressure, this is like modified specific volume, and you can imagine that for a perfect gas, both A and B, which are different constants, would have to be 0. So, van der Waals equation is one of the popular forms of representing real gas effects. Now, we are talking about molecules, molecular motion. So, if we really look at the thermodynamics of the system from the microscopic view or the molecular perspective, then we need to define it this way, that the gas is considered as a collection of particles in random motion, and the individual kinetic energy of each of the particles, they contribute to the overall energy of the gas. And if the particle is a molecule, it is not an atom, they can have rotational and vibrational energy modes as well, contributing to the overall energy of the gas. And also the motion of electrons in both atoms and molecules, they would be a source of energy, which is basically the electronic energy. It is there for the atoms as well as molecules, along with the kinetic energy that they possess. Therefore, the energy of a gas particle can consist of several different forms, and when summed over all the particles of the gas, they constitute the specific internal energy of the gas, which is small e per unit mass. The system, it is basically the internal energy per unit mass, that is basically the implication here. The system comprising of gas particles is in equilibrium when the particles are in a maximum state of randomness. Now, these will be better elaborated in the next week's lectures and subsequent lectures, where we talk about statistical thermodynamics aspects, where we delve more deeper into the molecular picture. From a macroscopic view, that is the classical thermodynamics point of view, the gas is considered as a continuum as long as the density of the gas is not too low, or we are not looking at very small length scales which are comparable with the mean free path. Equilibrium exists when there are no gradients in velocity, pressure or temperature, as well as chemical concentrations throughout the system, and this means that under equilibrium the system has uniform properties. For an equilibrium system of a real gas where intermolecular forces are important, and also for an equilibrium chemically reacting mixture of perfect gases, the internal energy is a function of both temperature and specific volume. So, there are differences with respect to a situation where it is a perfect gas. Similarly, it is true for enthalpy, which is given by H is equal to E plus PV. It is basically specific enthalpy, that is enthalpy per unit mass, and functionally they are represented this way. So, for both a real gas and a chemically reacting mixture of perfect gases, this functional form is true. If the gas is not chemically reacting and if we ignore intermolecular forces, the resulting system is a thermally perfect gas, where internal energy and enthalpy are functions of temperature only, and where the specific heats at constant volume and pressure are also functions of temperature only. Mind it that they are not constants when it is thermally perfect. If the specific heats are constant, the system is a calorically perfect gas. This is precisely the difference between thermally perfect and calorically perfect. In many compressible flow applications, the pressures and temperatures are moderate enough that the gas can be considered to be calorically perfect. And many of the relations that you have learned over the years in compressible aerodynamics are based on the calorically perfect gas assumption. Further, for a calorically perfect or a thermally perfect gas, that means it works for both. We have a couple of relations. They are, however, not valid for either a chemically reacting or a real gas. And therefore, keeping these in mind, the following relations hold, that Cp minus Cv is equal to R, where Cp is defined by the partial derivative of H with respect to T at constant pressure. Cv is partial derivative of specific internal energy with respect to temperature at constant specific volume. And from this equation, by dividing the left and the right hand sides by Cp, you get the gamma getting into the equation, which is the ratio of Cp by Cv, and also Cp and Cv getting defined in terms of gamma and R, R being the specific gas constant. So, these are very important relations, and it is good time to recapitulate these as you move along the course. If you are not able to recollect them well, then this is good time for you to go back to some basic books of thermodynamics and brush this up. We are going to do it in a rather concise manner here, but as a homework you have to keep doing this background study. Looking at first law of thermodynamics, it is written here for a closed system, and in this equation again E is a state variable, hence dE is an exact differential. It is not path dependent, its value depends only on the initial and final states of the system when it undergoes a process, while del Q and del W are process dependent or path dependent, and it depends exactly how you go from the initial to the final state following a particular kind of process. Some of the processes are mentioned below. Now, for a given differential change in internal energy, there are in general an infinite number of different processes which you can think of connecting those 2 points, state points, and thereby there are different ways of adding heat and the work done by the system. The 3 main types of processes which are very widely encountered when we discuss about compressible aerodynamics are adiabatic process, where there is no heat addition. So, there is no addition or rejection from the system, therefore, del Q is 0. A reversible process where there is no dissipative phenomena occurring which can lead to irreversible effects. Such effects can be due to viscosity, thermal conductivity and mass diffusion. If these are absent, then you have a reversible process, and an isentropic process which is both adiabatic and reversible. Now, for a reversible process, the del W expression happens to be minus P times dV, where dV is an incremental change in specific volume of the system due to an expansion or a compression, and it is basically due to displacement of the boundary of the system. And the del W expression has to be plugged into the first law equation, while the del Q is equal to 0, and thereby you have the expression for the first law in an isentropic process case as shown below. So, those are some of the basics associated with the first law. Coming to the second law, the equation states that the change in entropy during an incremental process is equal to the actual heat added divided by the temperature del Q by T plus a contribution from the irreversible dissipative phenomena of viscosity, thermal conductivity and mass diffusion, which may be occurring within the system. And as we already mentioned, that del Q may be added or subtracted from the system in an infinite possible ways, and it is basically path dependent. Additionally, entropy increases for chemical reactions occurring under non-equilibrium, which we will discuss later on, and these dissipative phenomena will always increase the entropy, which basically means that the Ts irreversible part is always greater than equal to 0. For reversible process, though, it is equal to 0, and a process always proceeds in a direction such that the entropy of the system which is undergoing the process plus that of the surroundings always increases, or at best it stays the same, it can never reduce. So, when there is no heat transfer, therefore, for adiabatic process you will have a ds greater than equal to 0. Now, if you look at the first law expression, if you substitute the del Q expression by that due to a reversible heat transfer, you will have T ds replacing del Q minus P dV equal to dE, and if you rearrange the equation, it becomes a form like this. If you bring in the definition for specific enthalpy, then it can be represented in terms of enthalpy, and then if integrated between states 1 and 2, you end up getting an expression for the change in entropy. We have made the assumption that the gas is calorically perfect for doing these calculations. Again, for isentropic equations, for calorically perfect gas, you need to set ds equal to 0, which means S2 minus S1 goes to 0, and thereby you end up getting relations of this form. And once you take them forward, they converge to certain relations expressing the pressure ratio, density ratio or temperature ratio for isentropic changes. These are very, very handy, for example, when you talk about isentropic flow through a CD nozzle and so on. Let us discuss a little bit about the perfect gas equation of state. We have already defined what a perfect gas is in terms of intermolecular forces, rather their absence, and we have also contrasted it with real gas effects or real gases where intermolecular forces are dominant. So, here we have a thermodynamic system which comprises of a pure gas, let us say a single species. It might be oxygen in its molecular form, or nitrogen or nitrogen dioxide or carbon dioxide or argon or any other pure gas single species that you can think of, and it has a volume of V confined within a certain system boundary. It has a mass m, pressure P and temperature T respectively, and based on this information, the perfect gas equation of state, which we may be referring in due course in abbreviation as EOS, is given by this very famous equation, which can be represented in different forms and has been postulated based on the works of several notable scientists. So, we first look at the equation and then take note of the scientists who have contributed. So, here is the equation P times V equal to m r t. We take note of the nomenclature, and the m is of course mass of the gas. In the italic form, you have the molecular weight or molar mass of the gas, and R is the specific gas constant, which is expressed in terms of the ratio of the universal gas constant and the molecular weight. Now, the equation of state has been postulated based on laboratory experiments performed by several notable scientists. Among them are Robert Boyle, Jacques Charles, Joseph Gay-Lussac, and John Dalton, spanning from 17th century to early 1800. And based on their experiments, it has been postulated. So, there is no way we can directly prove it in classical thermodynamics. There are ways of doing it in statistical or microscopic thermodynamics though. Now, if you divide the right hand side and left hand side by m, which is the mass, we would get P into V by m equal to P by rho, because mass over volume would give you density, and here you have the ratio. Therefore, it becomes P by rho, which is also equal to P times V, the specific volume, equal to R T. Therefore, we can write it also as P equal to rho R T. So, these are different possible equivalent forms of the perfect gas equation of state. Let us move on to some more forms. As we do that, let us take note of some more nomenclature here. Let us introduce the number of gas particles. We call them N. Molecular mass we have already introduced. We often refer to it as molecular weight also, or molar mass, and then the number of moles of the gas, which is given by the ratio of the mass by the molecular mass. Then comes the molar volume, which is nothing but the ratio of the V by N, the number of moles of the gas, and here the N of course is in italic form, and then comes the concentration, moles per unit volume, and it is incidentally inverse of the molar volume. So, those are very important expressions and nomenclature which need to be kept in mind. We recall the first form of the perfect gas equation we looked at in the previous slide, and from there if we make this readjustment on the right hand side, we are therefore able to express it in terms of the number of moles and the universal gas constant times T. So, the number of moles maps with this, the universal gas constant maps with this, and therefore, you now have a relation like this, P into V equal to, in italics, N R T. Now, if you take the N to the left hand side, then you can recall about this, the molar volume, and therefore, that comes into the equation, P into the molar volume equal to the universal gas constant into T. This molar volume, when we take a reciprocal of that, we can go to the concentration, because it is moles per unit volume, which is basically the reciprocal of molar volume itself, and then you are able to represent it as P by italic C equal to italic R T. So, you have P equal to C R T. So, this is another form. Now, the universal gas constant, we have stated it here. it is universal in the sense that it is the same for all gases, and its gas constant per mole of the gas, while the specific gas constant is going to change from gas to gas, and for air at standard conditions it is given by this value. We note that the universal gas constant has a value of 8314 joules per kg mole Kelvin. You have to be very careful about units here. So, there is a mole in the denominator, there is no moles existing here for the specific gas constant. It is basically the gas constant per unit mass, while this is the gas constant per mole of the gas. These are important facts that you have to keep track of, and this is obviously going to be different for different gases, because you are dividing the universal gas constant by the molecular weight in order to come to your specific gas constant. So, from the PV equal to nRT form, you can further change it to a form like this, where you divide it by the mass. Correspondingly, you will be able to introduce the specific volume here, and what you introduce on the right hand side, we introduce another nomenclature eta. It is mole mass ratio, the number of moles per unit mass of the gas, and therefore, you now have a form PV equal to eta RT. We have put a boundary here, a line demarcating the section on top and that we have at the bottom, because the one we have above the that demarcation is basically a continuation of the discussion of the previous slide. Why we have made that demarcation will become very evident over the next 1 or 2 slides. Now, coming to this form which we have derived earlier, PV equal to nRT, we now introduce the very famous Avogadro's number, which is the number of gas particles per mole, which is given by 6.02 into 10 to the power of 26 particles per kg mole, and that brings in a very important constant, the Boltzmann constant, which is basically the gas constant per particle of the gas. And then the K that we have, the Boltzmann constant, is nothing but the universal gas constant divided by the Avogadro's number, which is basically the number of gas particles per mole, while the italic n times Na gives us n, which is number of gas particles. So, again take care of the nomenclature that we have introduced over here. Based on these new introductions, we have the form PV equal to nKT, and further if you divide both the left and the right hand side by the volume, you will get a small n, the lowercase n into k into T, where the small n is nothing but number of gas particles per unit volume. So, we now have a fairly large number of forms of the equation of state. We can put them together in a very convenient manner over here, indicating that these are the different forms of equations of state that we have visited over the last few slides. We can classify them broadly based on mass basis, mole basis, or particle basis, and where, if you recall, the gas constants were different. One was the specific gas constant, the other was the universal gas constant, and the last one was the Boltzmann constant. And if you recall, these were the 3 forms we discussed about, where the specific gas constant was involved, while these were the 4 forms we discussed where the universal gas constant was introduced and used. And finally, these were the 2 forms we discussed in the context of the Boltzmann constant, the gas constant per particle of the gas. So, if you classify them into these 3 broad groups, then it will be much easier for you to track or keep them in mind. Now, if you were to talk about a mixture of perfect gases, then A typical mixture is what we find in air, where the main constituents are nitrogen and oxygen, and there are some trace gases including carbon dioxide, which is of course growing by the day. And then you need to talk about contribution of each one of the individual species of the perfect gases which constitute the mixture, and then we talk about the partial pressures of each of the constituent species. And when we sum the partial pressures, we end up getting the total pressure, and that is how we represent it. And the law which encompasses that is the famous Dalton's law of partial pressure, which defines the pressure of the mixture in terms of the individual species partial pressures. So, summation of species partial pressures gives you the total pressure as enunciated by the Dalton's law. Coming to the expression of equation of state in the case of mixture, this is how we have distinguished it. So, it is the mass based calculation, the mole based calculation, or the particle based calculation that we are talking about, like we had distinguished it in the previous slide. And you will thereby see the use of the R here in the specific gas constant sense, the universal gas constant sense, and the Boltzmann constant. And you see that for a single species, these are the forms that we have already talked about. The corresponding forms for the mixture of different species indicated with the subscript I. Similarly here as well as here. In terms of the densities of the species, you can define a lowercase c, which is not the same as the concentration, which is the uppercase c. So, you have to keep track of that difference, and that is called as the mass fraction. Let us conclude this lecture by saying that we recapitulated some of the elements of basic thermodynamics relevant for the upcoming lectures. We also recapitulated a bit of the boundary layer calculations on a flat plate, which helped us appreciate the need for discussion on high temperature gas dynamics. We discussed about different forms of the equation of state for a pure gas as well as a mixture. Thank you.